Welcome to lecture number 5. The subject of this lecture is almost classical ideal gases, which means that the ideal gases are quantum gases, but they have very low density and behave close to classical ideal gas. And our goal would be to find first leading corrections to classical ideal gases. What is the effect of quantum mechanics? This is the subject of this and contents of this lecture. I will start with grand potential for almost classical ideal gases. Then I consider first quantum correction to grand potential of classical ideal gas. I will introduce and prove theorem of small increments. From this theorem I will obtain hemoglobins potential for an almost classical ideal gas and will calculate pressure and thermal capacitance with almost classical ideal gas. I will finish with this lecture with historical bonus. I'll tell you very briefly about Wolfgang Pauli and his contribution to physics on the background of his time and tribulations. And Pauli has enormous significance for physics because this effect of non-classicality is due to quantum statistics introduced by Pauli and his principle of exclusion, of Pauli blocking. We'll start with internal energy on an ideal quantum gas obtained in lecture 4. So internal energy is integral of one particle energy over the number of particles. And this expression for it that we obtained, G is spin degeneracy, is 2s plus 1, with s is a spin of particle, v the volume of the system, m is the mass of the particle. This integral we obtain, it is in terms of epsilon, and mean epsilon is energy of one particle. Here upper and lower sign corresponds upper sign to fermions and lower sign to bosons. We'll consider both of them and results will be symmetric. One will be plus, second will be minus. We will be using a general relation between grand potential and internal energy, which is valid for any ideal quantum gas, either fermions or bosons. And this is a relation that I obtained for you in one of the first lectures on quantum gases. Omega is minus 2 over 3u. If I substitute this equation, I will obtain the following equation for omega. Simply multiply by 2 divided by 3, change sign, that's all. And then start calculating this expression. Initially, I will be doing everything exactly. Later, I will make corresponding approximations. So I will introduce variable z related to energy. This equation, epsilon is equal kBTz, correspondingly d epsilon is kBT dz. And I will introduce a notation x, which will be mu divided by kBT. Substituting, I will get to this equation. I will get, so power of kBT will be 3/2 from here and 1/2 from here, and 1 from here. So total power will be 5 over 2. So we see 5 over 2. All other quantities did not change. This is the only factor that I obtained. Multiplied by some function, which is this integral substituted. So it will be z to the power of 3/2 dz e to the power of z minus x. And x is produced by this mu divided by kBT is exactly s, x. And again, upper sign fermions and lower sign bosons. Let's go to the next slide. Now I will be introducing approximations. My main approximation will be that our quantum gas is almost classical. And my assumption will be this quantity x, mu over kBt, much less than -1, which means that mu is largely negative respect to kBt. So you will ask me why it corresponds to almost classical gas. I'll return to this point of the building theory. We'll show this is really approximation in which the thermodynamics becomes that of a purely classical gas. So this parameter characterizes your classicality when x is much less than -1. So large by modulus and negative. That is classical gas. Let us evaluate this function f of x. Again, I repeat its definition. What I will do, I will multiply numerator, denominator by exponential with the opposite exponent. So this will become 1, and this opposite exponent will appear here. Instead of 1 will be x minus z. And here x on minus z, the integral runs only over z. So x can be taken outside. And then this is a small quantity. Why? Because z is positive and x is negative. So this exponent is large and negative. So exponential is very, very small. Exponential is small. So I can expand. It will give me 1 minus plus this exponential. This is left from this factor. And I'm getting two, open up this parenthesis, I'm getting two integrals. So first is with 1, and the second is e power x minus z. And again, x is not a variable of integration, so e to the power of x can be taken out of integral. Give me e to the power of 2x, it's here. And I'm left with integral minus z minus 2z. And power is the same. So both these integrals can be expressed in terms of gamma function. The first integral is directly gamma function of 5/2. And this ex, so this corresponds to this 1, minus plus this second is this integral. Here I will denote 2z as a new variable. So I'm getting 1/2. The total power of this, it should be 5/2. So this is 1/2 in denominator, power of 5/2. And I'm left with extra x, e to the x. So 1 e to the x here, and the second here. So in this approximation, if I substitute this x, f of x is gamma of 5/2 exponential of mu divided by kBt, 1 minus plus 1 over 2 to the power 5/2, and another exponential. This exponential is small quantity. Now we calculate its coefficient gamma function of 5/2 with recurrence relation is 3/2 gamma of 3/2. And we know gamma of 3/2, it actually is Poisson integral, is value of square root of pi divided by 2. So together 3 pi to the power of 1/2 divided by 4. Now we recall equation 4, which I repeat here. Substitute. So this 3 will cancel this 3. This 4 goes to denominator and cancels this power of 1/2. This is 2/2 minus 1/2, 3/2. So I'm getting 2 to the power of 3/2 in denominator. Pi was power of 2 and square root power of 1/2. It is also power of 3/2 in denominator. So denominator contains 2 pi to the power of 3/2. This without change. 1 corresponds to classical value, classical limit, and this is the first quantum correction. So this sum of two terms and second term is exponentially small in the parameter exponential mu divided by kBt. Now we know that chemical potential mu divided by kBt is much less than -1, means that this quantity is exponentially small. This is, I am introducing notations. Omega is leading term and first quantum correction. A leading term is what comes from this 1, it's written here. Just repeat this formula. And omega 2 contains extra exponent. First, it contains sign minus plus. With this minus, it gives me plus minus. Now this exponential, as to this exponential, double mu. What about this coefficient? 2 to the power of 5/2 and 2 to the power of 3/2 is 2 to the power of 8/2 or 4. 2 to the power of 4 is 16. It's shown here. Everything else is without a change. Now again, to summarize by very meaning of our approximation, this is omega, a completely classical gas, and omega 2 is the leading quantum correction. We found the grand canonical potential of the system. Now we need to convert to the Helmholtz potential. Why do we need to do it? We need to do it to calculate standard thermodynamic quantities, which are kappa T and alpha. Kappa T is the coefficient of isothermal compressibility, and alpha is the coefficient of expansivity, isobaric expansivity. Cv, strictly speaking, is not a standard quantity. Standard quantity is Cp, but Cp is directly expressible in terms of Cv, kappa T, and alpha. The formula is known to you. It's one of the thermodynamic identities. It's exact formula. So these three quantities solve the problem. All these quantities are derivatives over either volume or temperature at a fixed number of particles, while omega would give you derivative at fixed mu, which is not the definition of coefficients. So we need to, from omega, to convert to Helmholtz potential, whose variables are T, V, and N. We want N. So we need to eliminate mu. We start with omega 1 that describes the classical limit, this one. We need to eliminate mu in terms of n. For this purpose, we find n. So by definition, n is d omega 1 over d mu at a constant Tv. This comes from definition of the omega potential. And we substitute this formula, minus changes sign to plus. Mu is only in one place, it's right here, so it is very simple derivative. It leaves the function the same because exponential still remains exponential. This gives the coefficient 1 over kBt from differentiation of this argument over mu. So instead of kBt 5/2 will be kBt 3/2. We get this nice ratio to the power of 3/2. It's remaining exponential. Now, what is important to understand? N and omega differ with minus sign and 1 degree of kBt. Everything else is n, right here. So omega 1 can be also written minus kBtn. Now I would like to bring to your attention fundamental difference between this omega and this omega. This omega expressed in terms of own variables of omega potential. This is not. So this is a fundamental relation and this equation of state. In fact, it is mechanical equation of state. As you know, omega is minus PV. So this reduces to PV, is equal kBTn, and this is what you precisely know, which you know is precisely true for a classical ideal gas. Now we take this equation, original equation, and resolve it with respect to mu. This gives me mu. It's very simple, of course. You divide by this, a logarithm, and multiply by kBt. This is what we have. Now we consider conditional applicability, what we are doing. So conditional applicability was mu divided by kBt much less than -1. It means that this logarithm is much less than -1, is negative. This argument is very small. This argument is much less than 1. This is what I'm writing, this conditional applicability. What I do, I resolve it with respect to kBt. It becomes kBt much greater than h squared divided by m v over n to third. And I don't take into account coefficients on order of 1, numerical coefficients. And this is understandable. This is a classical energy, thermal energy. It exists in classical physics. And h squared m, this is square of the distance between particles. Volume per particle to the power of 3 to the power of 1/3 is distance between them. And this is square of distance. H squared ma squared is the quantum mechanical localization energy. The conditional applicability means that thermal energy is much greater than quantum mechanical localization energy. Applicability condition implies that the particle density should be very small for the temperature given, and this is really the intuitively understandable condition. At a low particle density, particles don't feel each other. In quantum mechanics, the wave functions won't overlap, and they do not know anything about statistics. The only important wave functions overlap. So they should be close to each other to show the quantum properties. So now, in our case, in this approximation is purely ideal gas. Now we need to finish finding Hilbert's potential. So from thermodynamics we know its definition of omega potential differs from Hilbert's potential by Laplace transform in n. This inverse transform, so sign is plus. F is equal omega 1 plus mu n. So we have already obtained omega 1 in terms of TVN. It's simply minus kBTn. We only need to add this term. So this is n. The rest is expression for mu that we had in the previous slide. The only thing we'll do to bring it to a conventional form, we will use inverse quantity with respect to the gv over n mkbt by 2 pi h squared and change sign of logarithm minus. So these two terms will have the same sign minus. And this term will write as e here. E is the base of logarithm. So if we apply property of logarithm, logarithm of e is equal 1. So this gives me minus kBTn, this term. And this expression is exactly what we got using Gibbs canonical distribution for a classical ideal gas. So this term is really the limit, classical limit for ideal gas. And it doesn't matter for classical particle whether it's Fermi or Bose, this is exactly the same formula. And the leading correction F2 to the Hemoglobin's potential corresponding to correction omega 2 to grand potential given by equation 10 will involve the small correction theorem. This is a theorem very well known in statistical physics. And this is the formulation of the theorem as a formula. So if I have a change of a potential, any potential, say energy, any thermodynamic potential, say energy, what is this change? The change can be result of changing any parameters of the system. To say this magnetic field imposed on the system changes. There's electric field imposed on the system. Gravity changes. Or that may be formal parameter. Say the mass of an atom. It's a formal parameter. In real life, it doesn't change. I can change it, and energy will change. Or h bar, Planck constant, changed. You will change if I change Planck constant. That the latter has physical meaning. If I set h bar equal to 0, it is a classical limit. If I now set h bar value not equal 0 to real value, u will change. And this would be a small change for this specific case. And we can calculate it with this theorem. So delta u is change of internal energy of the system in response to change any of the controlling parameter, actual or a formal parameter, such as h bar, for example. This is corresponding change of Heimgoltz free energy. And this theorem states that they are equal. However, what you calculate free energy, you calculate internal energy at the values S, V, and N, and you calculate Heimgoltz potential at the value T, V, and N. So instead of S, argument is temperature, a temperature corresponding to this S. So temperature is derivative U over S. The same is true for small change of enthalpy, Gibbs free energy, and Grand potential. So change of any of these quantities in response to change of a controlling parameter, any controlling parameter, as long as these changes are small, are equal. So verbally, this theorem is formulated the following way. A small correction to any potential is the same quantity, just expressed in terms of the variables owned to this potential. And of course, U own variables SVN, FTVN, and so on. So proof of the theorem is actually straightforward and simple. Let us write differential of any two thermodynamic potential, say U and F. We start with U, and this is given TdS minus PdV plus mu dN. You know it from elementary thermodynamics. And there is also parameter L, lambda, on which everything depends. So if it parameter slightly changes, the change of U in response to this change is derivative U over lambda at a fixed every other variables S, V, and N, the lambda. So that's differential formula. Now let us take this potential U and do Legendre transform over the pair T and S. So you know TdS is equal to d of Ts minus S dt. And dTs I take to the left, and I'm getting to the left in the left-hand side dF. And the right-hand side TdS is replaced minus S dt. This is Heimgoltz free energy. And I do not do anything to this differential, or this differential. And from this, of course, I will get the dF over d lambda is equal to d over d lambda. This is the same quantity. I did not do anything to them. So these derivatives are equal for any two thermodynamic potentials. I can take not F but anything. So this is the result of this such a proof. And I will denote L multiplied by d lambda, each of these terms. And d over d lambda multiplied by d lambda at SVN constant is du. The same is valid for delta F, d over d lambda, delta H, dH over d lambda, and so on to the end. Now, taking this into account, I clearly see that these four quantities are equal as long as they express in terms of their own variables. Now let us return back to an almost classical ideal gas when F is equal to F1 plus F2. So Heimgoltz free energy consists of two parts. F1 is a classical limit, is Helmholtz potential of free energy over classical gas. And this is the leading quantum correction. The classical limit we know, given by equation 16, also we found it earlier in the course from Gibbs distribution. So the first quantum correction to the grand potential is given by equation 10. I'm just reproducing it here. And from the theorem of small correction follows, obtain F2, it is sufficient to take omega 2 and substitute mu in terms of T, V, and N. That's what it says. F2 of T, V, and N is omega 2 T, V, and mu when I substitute mu as a function of T, V, and N. So this is a simple approach, very general, it's true for any small change. We'll be using equation 11, which is expression for n, obtained as derivative of grand canonical potential in zero approximation. And equation 10 for the omega 2, which is the leading quantum correction to completely classical ideal gas. We'll transform the equation for F2. So what is F2? This is and 26 is simply F2. We need to substitute mu in terms of n. Let's do it. So this is F2. We obtained it. We will transform it. So we'll take GV n to the power of 3 half, kBt to the power of 3 half. kBt first power will be left, divided by 2 to the power of 3 half, and this is to the power of 2. This is 2 to the fourth power, so the 8 half, minus 3 half will be 5 half left, the coefficient will be 5 half, and this exponential mu over kBt is taken into account in this. So exponential mu, another exponential here, 2 times, so another exponential is left, and we'll substitute it directly from this equation. So this expression for this exponential, substitute it here, and again we'll have cancellations, have 2 to the power of 3 half, to power of 5 half. So what is left in denominator? 2 to the power of 2 half, в смысле 2, and this is this coefficient, kBtn. From this we get another n, so it will be n squared, and what is left, pi h squared n kBt to the power of 3 half. So this is the correction that we will be working with. In such a way, we finally get Helmholtz free energy. So this is one over completely ideal, completely classical ideal gas. And this is the first quantum correction we just obtained at the end of the previous slide. Now let's find what is small parameter. So small parameter is ratio this F2 to this F1, divide one by another, and at this point it's an estimate by order of magnitude. I drop all numerical coefficient, pi, 2, all of them I drop it, and that is this term, and one uncancels, so I'm getting n divided by v, this power 3 half in numerator, and in denominator I'm getting just this logarithm, because kBtn and kBtn cancel. So in this case, it is important to remember that this logarithm is large by formulation of the problem. So this is our approximation, logarithm is large. So if I remove it from denominator, I will increase the quantity, but not too much, because logarithm is never really large. So it's less than this numerator, and this is this numerator. And I will take n and v under this power. And this is construct known to us. It's h squared m. This is square of the distance between particles. So h squared m a squared is quantum mechanical localization energy divided by classical energy. The power of 3/2 much less than 1. And we assume that this ratio is by itself less than 1. So taking to 3/2 will make it even smaller. So it's certainly much less than 1. So this is our parameter of expansion. And as I mentioned already, we neglect coefficients, 2 pi and so on. And that's what I already told you. The expression of parentheses is the ratio of quantum mechanical energy, localization energy, to classical energy. Let us find the thermodynamics of the almost classical ideal gas with the first quantum correction. We'll find pressure and CV. We start with Helmholtz free potential. We repeat it here. And this again is the leading term. It describes completely classical gas. And this is the leading quantum correction. Let's find the expression for pressure. And this expression also is called mechanical equation of state. So P, pressure, is equal minus dF over dV, the constant T and N. So start differentiating this over V. V, in the first term, is only here. So give me simply 1 over V. I'm getting kBTN divided by V. This is this term. Now going to this term. Now V is here. So it gives me V squared in denominator. It changes sign. And it's another sign. So sign remains the same. And V becomes squared. I take 1V, kBT, N, and V outside. It is the same coefficient, this one. What I'm left, N first power divided by GV, because of V squared, and this coefficient without change. So this is the pressure. So this is pressure with, this is first quantum correction. So it's symmetric. For fermions, I'm getting increase of pressure, and for bosons, decrease of pressure by the same amount. Now let us go and find thermal equation of state, which means we're finding CV. For that purpose, we first will find entropy, and S is minus dF over dt, as we know from thermodynamics. We need to differentiate over temperature. Temperature enters the first term in two places. When I differentiate this T, I'm getting the same expression without T. When I differentiate over this T, I'm getting 1 over T. This T is cancelled. And with this minus sign, I'm getting 3/2 kBn. Now, when I differentiate this over T, this is T, and this is T to the power of 3/2. So result is T power 1/2 in denominator. T to the power minus 1/2. I differentiate it. I'm getting 3/2. And the coefficient 1/2 extra. So instead of 2 GV, I will get 4 GV, and this power is restored. So T is again to the power of 3/2. And this T, of course, disappeared. This expression for entropy. So I'm repeating this expression here. Now it's straightforward to calculate thermal capacitance. CV is T ds over dt at a constant V and M. And starting differentiating. So to differentiate this over dt is very simple. It gives me 1 over T, a coefficient of 3/2. This 1 over T cancels with this T. I'm simply getting 3/2 kBn. This is this term. This gives me 0 because it doesn't depend on temperature. This differentiation vanishes it. Now going here to differentiate this one. So T to the power of 3/2 give me minus 3/2, give me coefficient minus 3/2, minus changes sign from plus minus to minus plus, 3/2 coefficient I'll take outside, it's a common multiplier, give me t in the denominator to the power of 5/2, and this t restores back power to 3/2. So this parenthesis, this combination is exactly the same, and I'm getting very concise and beautiful result. So correction to CV is also symmetric, but in this case for fermions we get less than for bosons. For bosons we get more. So pressure and thermal capacitance behave in a sense, with respect to quantum corrections, opposite ways. Quantum corrections increase pressure but decrease CV. So what is physical meaning of these results? We'll discuss it on the next slide. So for pressure, the quantum correction is positive for fermions and negative for bosons. This can be understood. Fermi statistics, which implies Pauli exclusion or blocking principle, I'll discuss it in the next slide. Not discuss, but tell you story in the next slide, forbids two more fermions to occupy the same state. The four fermions tend to occupy different states. So to decrease energy, the first occupies states with small momenta, and then states with higher momenta, because they cannot all go to small momenta. It's prohibited by the statistics. And going to higher momenta increases pressure. To the contrary, bosons tend to occupy together states. There's no problem occupying many of them in the same state. And of course, they occupy states with a lower momenta because they have to decrease their energy. This would correspond to equilibrium, minimum free energy. Ultimately, if you decrease temperature a lot, you'll get both condensates, which happens at a low pressure and high density, and all of them will go to states zero momentum. So this such a preferential accumulation states with low momentum leads to reduced pressure. Now the same population distribution, however, yield opposite signs of quantum corrections for CV. It also can be understood. So CV, in contrast to pressure, CV is defined as an increase of energy per unit increase of temperature. That was not in pressure. For unit increase of temperature. Now, what if happens if I increase temperature? So the particles in their distribution tend to move to high energy state because they have to increase the energy. Such as changes hindered for fermions. Imagine fermions somewhere in the middle of the pack. It needs to go up and some state above are occupied. It cannot occupy them. And that Pauli blocking excludes such transitions. And therefore, the system doesn't take that much energy. On the other hand, for bosons, there is no such blocking. Moreover, they tend to occupy states already occupied, so they can easily move up. So that qualitatively describes the signs of these corrections. Next slide. So this is a bonus in a sense. A bit of history. Who was Wolfgang Pauli? What was his time? What else did he do in science? So let me tell you. So this is very brief overview of his life. He was born in Vienna, Austria, or Wien as they say, in 1900, just at the beginning of the 20th century. He died very young, relatively young actually, at the age of 58. Today I would say very young. In Switzerland, Zurich, German-speaking Switzerland. He was citizen of Austria, and then became citizen of the United States and Switzerland. He his alma mater, university from which he graduated, was Ludwig Maximilians University of Munich. And I know this university very well. Actually, I was 2 years a professor there at Munich. It was a wonderful time. However, life called me to go back to Atlanta. So this university was place of scientific birth of many outstanding scientists. One of them was Pauli. So what did he do? Pauli exclusion principle, we just mentioned it. Pauli-Willis regularization, I don't know what it is. Pauli matrices, I know them perfectly well, and you should know from the quantum mechanics. Don't know what is meant by Pauli effect. Pauli equation is equation for the particle with the spin. Pauli repulsion is a repulsion of two electrons in the same state, because they cannot, if I bring them together, they will be occupied in the same state, and this is forbidden. Pauli paramagnetism. Pauli paramagnetism will be studying in the next lecture, in fact. This Pauli paramagnetism and Landau diamagnetism we will get in the next lecture, I promise you. Pauli-Lubansky pseudovector, I don't know what it is. Maybe I know under different name. I didn't try to find everything here. He did a lot. And he coined the phrase. It was very negative. He had very sharp tongue. So when he says something so wrong, he tells, oh, this is not even wrong. He coined the phrase. He got a number of awards. Relatively early in his career, he got Heitzinger Prize, no idea what it is. Lawrence Medal, it's distinguished award. Next was the greatest award possible. It's a Nobel Prize in Physics, 1945, was given to him for Pauli exclusion principle. I don't know. This is the Royal Society award. I don't know precisely. Matteucci medal is Italian medal. Max Planck medal is a medal award, is the highest award of Max Planck Society in Germany. So what's his biography? As I told you, he was born in Vienna to a scientist, Wolfgang Joseph Pauli, who was born Wolf Pascheles. Wolf is typically a Jewish name. So he changed his name to German, Wolfgang. His wife and his mother was Berta Camilla Schutz. His sister was Herta Pauli, writer and actress. Middle name of Pauli was given in honor of his godfather, Ernst Mach, famous scientist in his own right. Pauli paternal grandparents were from prominent Jewish family of Prague, in Czech Republic now, at that time Czechoslovakia. His great-grandfather was Jewish publisher Wolf Pascheles, same name as his. Pauli's father converted from Judaism to Roman Catholicism, just shortly before marriage and birth of Wolfgang. So Pauli was raised as a Roman Catholic. Eventually he left the church and he was going to become mystic, to mysticism, such a direction. Kind of religion, a sect. Pauli attended the distinguished gymnasium in Vienna, graduated with distinction. But even more distinct than that, only 2 months after graduation from gymnasium, Jesuit high school, he published his first paper on Albert Einstein theory of general relativity. This is one of the most difficult areas in physics, especially at that time, especially for somebody who was 19-year-old, just graduated from high school. Then he attended Ludwig Maximilians University in Munich, working under Ernst Sommerfeld. Sommerfeld is characterized as the last greatest physicist of classical physics, and next was quantum era, which Pauli so brilliantly developed. And by the way, before I'm going further, I'll tell you that Arnold Sommerfeld, when he asked question, what is your greatest discovery in science, always would answer, my greatest discovery in science is Wolfgang Pauli. So Pauli received his PhD 1921. This is very interesting. So Germany was annexed by Austria. They call it Anschluss in 1938, and Pauli became a German citizen. It's a problem for him because he has 50% of Jewish blood, and Germans, the Nazis, won't look at your religion. 50% is shaky. They can kill him. So he left between 1939 and 1940. And 1940, he went to Switzerland and tried to get Swiss citizenship. He worked at ETH. It is Technical University at Zurich. Genossische Technische Hochschule, which means public technical high school, literally. Pauli moved to the United States in 1940 when Swiss denied his citizenship, and he was employed as a professor theoretical physics of Institute of Advanced Study. So he basically overlapped with Einstein. 1945 he got Nobel Prize, as we know. 1946 war was finished, and he became citizen of the United States. But same year he returned to Zurich. Finally he got Swiss citizenship in 1949. 1958 Pauli was awarded Max Planck Medal. It was his last award. The same year he fell ill with pancreatic cancer. It's a very aggressive cancer, and died the same year. So if you contrast him to his colleagues who took flight from Nazi Europe because of Jewish origins, and those Amelia Segre, who was Jewish, Enrico Fermi, whose wife was Jewish, Hans Bethe, who is converted Jewish, Albert Einstein, who did not actually exercise Judaism, but by birth was Jewish, and Leo Szilard, who was Jewish. So all these famous people, there's quite a few of them, Nobel Prize winners. Segre, Fermi, Bethe, Einstein. I'm not sure about Szilard, he may be too. Pauli was not a participant in the struggle against Nazism. He didn't fight them. He just worked. And he didn't participate in the Manhattan Project. All others did. So, next lecture, we will be studying magnetism of electrons. Now we return back to the scientific heritage of Pauli. And here I want to show you the famous paper. It was published 15th of October 1940. And the title of the paper was The Connection Between Spin and Statistics. This is the famous eternal Pauli theorem. This is for which he got Nobel Prize. That predicts the Pauli exclusion principle or Pauli blocking. Now what I want to, you can look through that. What I want to bring to attention date is 15th of October 1940. The Second World War started with the Germans attacking Poland. It happened 1st of September 1939. So it's a little more than only 1 year after war started. He just moved to Switzerland and already got for himself position at Princeton. He published this paper. It was the most difficult time. He was running from Nazis. He couldn't get citizenship in Switzerland. He had to move to the United States, to a completely new place. As a result of that, he published one of the most significant papers in the history of science, theorem about connection between spin and statistics, which you use every day, and then spin, half integer spin, tells you that particle belongs to Fermi-Dirac statistics, and integer spin is Bose-Einstein statistics. The theory was established by Pauli, and in this specific paper, you may wish to take it from the library, try to read it. I tried it, by the way, not extremely easy paper. Not because contents is very difficult. Problem is that today all notations changed, technique changed. And we now do not use imaginary component of a 4-vector. Now we use real, but we do not use the Euclidean matrix. We use Riemann matrix. Euclidean matrix, the diagonal coefficients 1, 1, 1, 1 in 4-dimensional space. And in the Riemann, it is 1, 1, 1, and minus 1. And that minus 1 is time. So we can read it. It's a beautiful paper. And that completes this lecture.